We will now introduce scalar surface integrals. The setup is pretty much very similar to scalar line integrals. So suppose that we have a 3D domain, and inside in this 3D domain lies a surface S, and the function f is defined on that domain. Again, strictly speaking, we just need the function f to be defined on the surface S. And of course, we want it to be continuous. Then this will be a function of 3 variables, of course. And what we would like to do, at least from the point of view of the method of exhaustion, is to actually subdivide the surface into very, very small pieces. On each piece, choose one point, and pretty much form a sum that where we take the value of the point and we multiply it by the area of the corresponding piece, and we add all of this. And as the subdivisions become smaller and smaller, this will tend to a number that we call the scalar surface integral of the function f on the surface S. Now, we should expect this whole process to be quite analogous to what we did in the case of scalar line integrals. And it might be a good idea to recall what we did in that case. So in that case, we had our path C. We wanted to compute the scalar line integral of f along C. And for that, we needed a parameterization from an interval AB. And eventually, this integral ended up being the integral from A to B of f of r of t times the speed integrated from A to B, where AB was the interval of the parameterization. We should expect to have something very similar going on here. And here's how this is going to work. We will still have a parameterization over coming from a domain D in the UV plane. We would like to keep our variables separate. So the way we had T for the parameterization of the path, the variable of the parameterization of the path, we use U and V. This is not a very strict assumption, and occasionally it's going to be bent. But we think of a vector valued function taking 3-dimensional vectors as its outputs that is defined on D. The fact that we consider it as a vector valued function is pretty much similar to parameterizing paths using vector valued functions. So in those cases, we really consider the vectors as position vectors originating at 0, 0, 0. That's exactly what happens here. And now the formula is going to look very similar, except that we have to ask ourselves, what was this approximating in the case of the paths? And the answer is the length of the path, both at a given point and if we take the integral over a small part, that would have given us exactly the length of the path. So here, we will need a similar term. And the question is, how is this term going to be formed? And basically what we need is an approximation of the area of this little part of the surface. And I should magnify this in order to show what is going to happen here. So you have this surface is curved in some sense. However, what we do is we take the tangent vectors. And when we take the tangent vectors, which can be obtained as partial derivatives of the parameterization, the same way that the velocity serves as the derivative of the parameterization in one variable. When we do that, then the area of this parallelogram, which can be thought of to be very close to the area of the surface patch of this small part of the surface, is equal to the magnitude of the cross product of the two vectors. And it's exactly this component which is going to appear in our integral. And we're going to express this component by considering the cross product itself, which is a normal vector on the surface. Since it's perpendicular to the plane generated by the two tangent vectors, it's going to be normal on the surface. And later we will see that this will have a much more interesting use in the case of vector surface integrals that we should expect them to be introduced. So it's exactly this vector that we're going to consider. And now we're ready to give the formula. And the formula is going to be, so this is going to be a double integral defined on the domain of the parameterization, that's the domain D that we consider right here, of the pullback of the function on the domain of the parameterization by means of the parameterization, multiplied by the magnitude, and this is not dot, this is common multiplication by the magnitude of the normal vector that is generated through this parameterization. And that's our formula. And this should be considered to be in full analogy with this. And that's what scalar surface integrals are. So let's take a look at an example. So as an example, compute the scalar surface integral of f of x. Actually, here I should just write the integral. That might be a better idea. The scalar surface integral actually in the previous case, since this is a surface integral, I should be using a double integral as my sign. So so we will have the scalar surface integral of xy plus z ds along S, where S is the part of of the plane x plus y plus z equals 3 that lies over 0, 1 cross 0. Okay, so let's see how we would do something like this. So first of all, let's get an idea about what the domain looks like. So here we have this very nice plane that intersects each axis at the point 3. And somewhere here we have the square 0, 1 cross 0, 1. So we really want the portion of the plane that lies above 0, 1 cross 0, 1. It should be drawn a little larger actually than this, something like this. So the important thing here is what would be a parameterization, and we haven't done many parameterizations of surfaces, but every time we can think of that surface as a graph, we should be able to find the parameterization pretty easily. So here, the plane in which this quadrilateral lies is x plus y plus z is equal to 3. And we can easily solve for z. So this gives us 3 minus x minus y. And that means that this plane can be considered as the graph of the function f of xy equals 3 minus x minus y. So we have a graph parameterization that will be, how do we form graph parameterizations? We juxtapose the independent variables with the dependent ones. And the domain of this parameterization is simply the projection of the surface onto the xy plane, meaning 0, 1 cross 0, 1. Now, the underlying function here is f of x, y, z equal to xy plus z. And we can actually compute everything now. So let's pull back the function onto the domain of the parameterization. This simply means that wherever we see an x, we replace it by u. Wherever we see a v, we replace it with a y, we replace it with v. Wherever we see a z, we replace it with 3 minus u minus v. So this is going to be uv plus 3 minus u minus v. So this is the pullback of the function on the domain of the parameterization. And what else do we need? We need the normal vector. So the normal vector would be g sub u cross g sub v. What do we mean by g sub u? By g sub u, we mean that we take g of uv and we differentiate all the components with respect to u partially. So this will give us 1, 0, negative 1, cross 0, 1, negative 1. And this will be ijk 1, 0, negative 1, 0, 1, negative 1. And this will be 1, and then there is again 1 and again 1. And what we really need from here, so I should have said that this is n of uv, so the normal vector. We need the magnitude of n of uv, which in this case it's constant. We shouldn't expect the things that we get here to be constant, but here we got really lucky. So now we're able to put everything together. So it will be the double integral over the domain of the parameterization D of the pullback of the function, so uv plus 3 minus u minus v, times the length of the normal vector, which is square root of 3, dA, and this will be the integral 0, 1 to 0, 1, uv plus 3 minus u minus v, all multiplied by square root of 3 du dv. And this cannot be such a hard integration. In fact, if we carry out the integration, what we're going to get is 1/4 plus 3 minus 1/2 minus 1/2. And this can be computed to be square root of 3 times 9/4. And we can leave it like that. There's no further simplification that we can apply here. So let's recap, because it might seem at first like an overwhelming task, but we need to compartmentalize the different parts and focus on what needs to be done here. And of course, the most important part here is the parameterization part. Very often we will have this opportunity of being able to apply a graph parameterization. And once we have the parameterization, we need to really compute the normal vector. We need to put together the pullback of the function and then multiply the pullback of the function with the magnitude of the normal vector and just compute the resulting integral over the domain of the parameterization. Again, it might seem that there are many steps involved here, but it's not such a hard thing to learn, especially if we're already used to the scalar line integrals that had a very similar workflow. Now, we have a very special and interesting case of this whole process, which is the case of integrating the function 1. In general, in most integration theories, when you integrate the function 1, you find the measure of the domain of integration. And here, that measure is going to be the surface area. So it turns out that the double integral of the function 1 ds along S is nothing else but the surface area of S. And this can be thought of as actually the definition of the surface area. It's not like we had a way of measuring the surface area before. And pretty much what is going to happen is that once we have a parameterization and this produces a certain normal vector, which is obtained this way, then this integral is going to end up being the double integral over d of the magnitude of this normal vector. And it turns out that this can be computed quite easily in the case that the surface patch can be thought of to be a graph of a function of two variables. So let's say that z here is f of x, y. Then the parameterization that we can have is going to be g of uv equals u comma v comma f of uv. And if we take the normal vector, we're going to find 1, 0, f sub u cross 0, 1, f sub v, and when we find this determinant, this will end up being minus f sub u, the middle component minus, f sub u. The middle component is going to be minus f sub v. And the last component is 1, which means that the magnitude is going to be square root of f sub u square plus f sub v square plus 1. And now here's a very interesting remark that simplifies this whole story once we see what the answer is. Obviously, we consider the function f of u comma v, which was obtained from f of xy by replacing x and y by u and v if we want it to be consistent. But now that we see what the formula is, there's actually no reason to have made that change, which means that we come up with the following general formula. The surface area of the graph of f of xy over the domain D equals the double integral over D of square root of 1 plus f sub x squared plus f sub y squared dA. And this is a formula that is not hard to remember. It's actually very similar to the arc length formula that one learns in a standard calculus 2 course. But let's see an example so as to see how this would work. So example, find the surface area of the part of z equals 4 minus x squared minus y squared that lies above the xy plane. So here we should notice that this is already given as a graph. So this can be thought of as the graph of f of xy is equal to 4 minus x squared minus y squared over the set of all xy. So remember, we want z to be greater than or equal to 0, which means 4 minus x squared minus y squared has to be greater than or equal to 0. And this is simply the disk of radius 2 centered at the origin, 0, 0. I mean, if you solve this inequality, you will get x squared plus y squared is less than or equal to 4. So the surface area if we call this domain D, is going to be the double integral of D of square root of 1 plus f sub x squared plus f sub y squared dA over this domain D. And how much is f sub x squared? Well, this is your function, so f sub x squared is negative 2x. So this will give you 1 plus 4x squared, and similarly plus 4y squared. And now the question is, once we have come up with this double integral, how do we integrate it? The domain is a disk, so we shouldn't think twice before turning to polar coordinates. So this will be 0 to 2 dr, 0 to 2 pi d theta, since we're going all around. We have square root of 1 plus, well, the quantity here is 4 times x squared plus y squared. And we know that in polar coordinates, x squared plus y squared is r squared. So 1 plus 4r squared. This takes care of the integrand. And of course, we shouldn't forget the Jacobian. Obviously, this integral will split. It's a very simple integration, no matter how you look at it, once you realize that a substitution will be needed. So you have the integral from 0 to 2 pi d theta, which is, of course, 2 pi. And then you have the integral from 0 to 2 of square root of 1 plus 4r squared times r dr. How do you compute this integral? Set u is equal to 1 plus 4r squared, and du is going to be 8r dr, and r dr is going to be 1/8 du. And so this integral will end up being the integral of square root of u. We need to put 1/8 here, du, and now we have to be very careful with the endpoints. What are the endpoints? We're supposed to take the limits of the previous integration and plug them into the substitution. So this will give us 1 all the way to 17. And the antiderivative of square root of u being u to the 1/2, is 2/3 u to the 3/2, and this has to go from 1 to 17. And we should not, of course, forget the 1/8 that we have here. And that will give us 1 over 12 of 17 to the 3/2 minus 1. Don't forget that this was just the second factor. So when we multiply things together here, we will have pi over 6 times 17 to the 3/2. 17 to the 3/2 is 17 times square root of 17. So 17 to the 3/2 minus 1. And that's the actual surface area that we were looking for. So we're coming up with many interesting formulas, and we should finish here because these are two good examples of scalar surface integrals, but we should be back with some more examples before we delve into vector surface integrals. And that's all. Thanks for watching.